Ah, welcome, students. I'm going to talk about section 7.1, estimating a population proportion. My students who are with me are going to act very surprised as I read this through, even though I've just done it a moment ago. I always forget to turn on the record button, just bugs. In any case, we're going to take a look at sample size. And this notion of sample size determination has to happen prior or before any sampling. I need to know how large of a sample I might need before I go out and gather that sample. And there's two things I need to take into account. The first, what kind of level of confidence do I want for my study? What kind of confidence do I want to have in the confidence interval I'm going to build? I do know that a higher level of confidence means a larger sample, and I do know larger samples are more expensive. Basically, the levels of confidence I'll be choosing from are 90, 95, or 99%. Other situations do indeed use other levels of confidence, but for our semester, that's a fine group. Now, once I know what that level of confidence I want to attain is, then I also need to know what level of accuracy do I want? In other words, what margin of error will I accept? So I need a margin of error too. What percentage of error, perhaps, if we're working with proportions, or units if we're not, might I be willing to tolerate? So I need to know my margin of error as well as my level of significance. I must know E. Now, those two things really give me enough to get started on that question. Now, here's the deal. This is one of the few times we're actually going to need a couple of formulas. It's the only time in chapter 7 that we need them, but we're going to need them tonight. So I'm going to talk about and do a little bit of algebra. We do very little this semester, but we're going to do a little bit today. Now, I'm going to put up my expression for the margin of error. So when I'm estimating a population proportion, my formula from last night looked like E equals Z alpha over 2 times the square root of P hat times Q hat all over N. Now, that's an equation that contains a sample size, a value that depends on the level of significance, and a margin of error. It also contains something else, and I'll talk about those in just a moment. So the first thing I do is I'll solve this for n, dividing both sides by my z alpha over 2. I have p hat times q hat all over n. That's still in a radical, but I'll eliminate that radical by squaring both sides. We have a ratio on the left, so that's ze squared divided by the z alpha over 2 squared. On the right-hand side, we have the p hat, the q hat, and the n. Now, at this point, I can multiply both sides by n to clear that fraction and by the reciprocal of this object here. So the reciprocal, z alpha over 2 squared divided by e squared. Through the wonder of cancellation, the ends cancel there. The e squared's over here, the z alpha over 2 squared's over there, and we have n equals z alpha over 2 squared times p hat times q hat all over e squared. And this is a formula that I can use. There's only one thing weird about it, and I'm going to go into that on my next sheet here. So I have n equals z alpha over 2 squared times a p hat times a q hat all over an e squared. Now, here's the problem with this particular formula. The problem with this formula is it relies on a sample. And didn't I just say this is something we do before we take any samples? So how can I have a sample stuff in there? The point is I really can if I'm super ignorant about the topic at hand. So I have to deal with that right there. And we deal with that by making a simple assumption. If I know nothing about P and Q in my population at large, I'm going to assume that both in the population and in my sample, P hat and Q hat are equal. That's the most harmonious assumption I can make. And if those two are equal, then I know, because these are probabilities and it's only two outcomes in general to work with, I know that if I add them together, I have to have a total of 1. Now, if they're going to be equal and they have to sum to 1, that means P hat is the same as Q hat is the same as 1/2, because 1/2 plus 1/2 equals 1. So when I plug that into my formula up there, 1/2 times 1/2 is 1/4, or 0.25. So the formula that I'll start with is n equals z alpha over 2 squared times 0.25 divided by e squared. This is my sample size formula when I know nothing about the proportions I am working with. So let me start to summarize, and then I need to go back to this equation here. So if we know nothing about P hat and Q hat, n equals z alpha over 2 squared times a 0.25 divided by an e squared. And that's the formula we use. However, sometimes we have previous work or previous data to work with. And if I have data on P hat and Q hat, this is, again, it's only sometimes I have that data. If I have that data, I can then use that in that first form of that formula, P hat, Q hat up here divided by E squared. And the problems are very specific. The problems will say, we know nothing about P and Q, and you're supposed to use this formula. Or the problem may say something like, previous study shows P hat and Q hat are close to, and they'll give you a couple of values. So we can use then this formula with those values. But you got to be on the lookout for it, but it's not really hidden. So because it's not really hidden, you should be able to figure out which one of these two formulas to work with. Now, there's a couple of things that we need note that we need a z alpha over 2. That's a critical value that we were talking about last night. So because we need a z alpha over 2, I will have to use that inverse normal tool to find that value. And I'll run through those examples in just a moment. But other than that, we need the inverse normal tool. Other than that, we need one of these two formulas depending on the scenario. So let me run through an example, and then we'll come up against the weirdest little aspect of this rule or this process. So so we're going to estimate a proportion. That's P. So we're going to go out and gather a sample. We want to determine the sample size for a 95% confidence interval with a 4% 4% margin of error. Nothing is known about P hat or Q hat. So this is your basic type of determine the sample size. It'll actually say those words somewhere in the problem, determine the sample size. And I'll need to remember which one of those formulas to use. I'm going to make you go away for a second and bring these guys back for a moment. If we know nothing about P hat and Q hat, I use that assumption that I detailed a moment ago. So this is the formula I'm going to use. I'm not going to use that formula at all. It's really pretty much a straightforward process. As I say, they've got to tell you about some very basic detail. They have to tell you the level of confidence you're going to need. That's a 95% level of confidence. And they also need to tell you your margin of error. So 95% level of confidence, E is equal to 4%, 0.04. This will be 0.95 if and when I need that. Now, let me go ahead and run through the process of taking care of that. Let me note those values over here. All right, so the first thing I always go after is the Z alpha over 2. So the critical values, and you'll remember from last night's discussion, when we build a confidence interval, we get 2 of them. So this is my Z distribution, because that's the distribution we use for this particular type of problem. We have the 0 there. We remember our mean is 0, our standard deviation is 1. We know the area underneath the curve is equal to 1 because it represents probability. So I'll be finding 2 critical values there. Now, 95% of that area, or 0.95, is wrapped up there in your middle. Your margin of error, 95, excuse me, your level of significance, 95%, means that alpha is 5%. That's going to give us our borderline of significant from insignificant scores. And I need to remember that 5% is split in half. So 0.05 over 2, 0.05 over 2. And I'm going to use those values with my inverse normal tool. So let me jump over to my calculator and run through those calculations. Because I'm not sure exactly what people have, because depending on the version of your TI-84, you go a couple of different ways with the keystrokes. So let's see, let me share. There we are. All right, so let me see. My stat wizard is turned on. Good, that's the way I want to start. And then I'll do the same problem a second time with it turned off. Now, if I take a look at that distribution tool and find my inverse normal, I can do this a couple of different ways. If I'm constructing a confidence interval or I'm working with a sample size question here in 7.1, I definitely like this setup. 0.95 is the amount of area in the center of that graph. Remember, I draw these quick graphs to help me figure out exactly what it is I need to put into these tools. 0 and 1 for the important pieces. If the center hadn't been selected, I would select it there. And at that point, I would paste it into my inverse norm function. And you'll note that I get two distinct values. There's a negative value and then there's a positive value. I usually round these to 3 decimal places. So it's a 1.959. That means this really needs to be looked at. So 960 or 96. Let me just make a note of that over here. Plus and minus 1.96. Now, suppose you didn't have one of these newer versions of the TI-84. So I've turned off my stat wizard, and now when I go ahead and I pick up my inverse norm function, I'm directly there. Now, when it's set up in this mode and you have one of your older TIs, you really need to input your area as measured from the left. So that little bit of area, let me stop my sharing for just a moment. This little bit of area here, 0.05 divided by 2. Now, some of you, I'm sure, can get to the correct decimal value of 2.5 cents, if you will, without a problem. Other people might have an issue with that. If you remember divide by 2, your calculator is more than happy to help. So I'll type in 0.05 divided by 2. I said 0.05 divided by 2, comma, then the mean, then the standard deviation, excuse me, for the Z distribution. So there we go. The values are in there. And I'll get this value over here, the negative 0.959 and change. See, there it is. So if my calculator is working in this mode, as opposed to giving me the 2 values, I always go for that one on the left. And then I use the symmetry of the Z distribution to take this negative 1.96 and realize this value over here is a positive 1.96. So however I get them, I need to make sure I get the correct 2 critical values. Which one I use doesn't matter because that formula has a square in it. So n equals 1.96 squared times 0.25 divided by my margin of error squared. You've got to remember to square the critical value and the margin of error. If you square a negative, it becomes positive. If you square a positive, it stays positive. It really doesn't matter which one you use, but if you use a negative, you got to appreciate the notation or you can end up in the wrong place. So there we go. Let me go ahead and jump back to Mr. Calculator. And I will type in. And now here again, order of operations can play a big issue in how things go into a calculator. But once again, for whatever reason, the formulas we encounter are very, very kind to students. So 1.96 squared times 0.25 divided by 0.04 squared. So you can see that it goes in there smooth as butter, and I end up with a 600.25. Now remember, this is a sample size. We are going to have to go out and collect or measure that many objects. Is there a problem with the 600.25? Well, yes, you can't measure 0.25 of an object. You're going to measure either 600 or 601 if you have a sample. That's your n. Your n can't be fractional. That is as discrete as any number comes, 0 to whatever. Count by ones. And now we get to the really, really weird part of all of this that sometimes students will forget. And to be honest, I will test you on this. That number there is a minimum. I cannot go below that number. So if I was to follow my usual rule for rounding, I'd end up with a 600, but not this time. I can't go below that, otherwise I won't have the level of accuracy that I need. So my sample size here is 601. If you're going to have to round this, if for some reason that's not a whole number, and it won't be most of the time, you're going to need to round this up. And that can throw students because, oh, I'm breaking the rules. No, you're not breaking the rules. That number there is a minimum value. You cannot go below that, but you've got to have a whole number. So it's got to be rounded up. Even if it was 600.01, I still would write 601. So I hope that's clear, because that can be a real issue. Because I will give you, if you see this kind of question on your quizzes and exams, I will give you the choice between 600 and 601. And I will expect you to choose or hope that you would choose the 601, because you would remember the rounding rule. So it's a little bit of an oddity. It really is, but there we go. Now, what changes in this problem? Well, I can ask for different level of accuracies, but let me give you another example. We're again going to find sample size. Well, this time we're going to go with a 90% level of confidence. And we want a margin of error equal to, let's make it 2% this time instead of 4%. So I've got my level of confidence. I've got my margin of error. And by the way, I only look at these problems in section 7.1. This is when we are working on sample size for a proportion. If we're working with something else like a mean, there's different formulas, but I think this is going to usually be enough for our purposes. So this problem is a little bit different. This problem tells me that in previous research, I have no idea what I'm studying, by the way. p hat is equal to, oh, I don't know, 0.37, and q hat is 0.63. They've got to add up to 1. So I have some previous work to look at. And we often actually have this because we like to see how things change over time. I'm thinking of how, for example, political polls on elections. There'll be poll after poll after poll, and they'll change slightly or maybe a lot over time. So here again, what I need is my critical values. This time the area in question is 0.10 divided by 2. So z will equal plus or minus. And I'll come over here to my calculator and I'll run through that calculation. I believe I still have my stat wizard turned off. So I'll enter in that area that's off there to the right. That is, excuse me, to the left, 0.10 divided by 2. Yes, that is 5%. Not hard to get to, by the way. There we go. Blow on it once for luck. And a negative 1.645. So I've got my two critical values. There they are right there. I have my margin of error, 0.02. That's the 2% in decimal form. So my sample size, n equals 1.645 squared times a 0.37 times a 0.63. Divide all of that by the 0.02 squared. And that will give me my sample size once I round up to the nearest whole number. Now, it's possible that might come out to be a whole number. That's fine, but it rarely happens. I don't count on it. Common mistakes here are to forget the square. Let's see, 0.37, 0.63 divided by 0.02. Square that little puppy. Again, the order of operations, that'll take care of the entire numerator stuff and then divide by that. And by the way, if you remember your order of operations, exponents are done first. So it'll take care of the squares and then it'll multiply and divide in order from left to right. There we go. 1,576.93, 1,577. Let me stop my sharing. So 1,577. So there we go. You really do need the formula and you need the inverse norm tool to get to the critical values. So there we go. In terms of our sample size, you've now seen everything that you'll ever encounter in your homework or on your quizzes and exams. But there is one or two other things I want to point out. Three other things, actually, I want to point out before I leave this topic. Excuse me. I want to talk about critical values, specifically these z-scores. These critical values that we've been using are kind of locked in stone. For example, that last one that we looked at for your 90% level of confidence with a margin of error of 10%, those values were z equals 1 plus or minus 1.645. For my 95% confidence interval, my z values were plus or minus 1.960 or 1.96. These don't change. I do feel compelled, though, to point out that when we get to the 99% level of confidence, there's a bit of an issue. So let me run through the keystrokes, and I'll let you know, and you can tell me what you think about the issue. So back over to my calculator. Clear you out. In fact, let me turn my stat wizard on. It makes the keystrokes just a little bit easier. And then I can just talk about what we see here. So back to the inverse norm. 0.99, that's the 99% in the middle. Oh dear, no, come on, there we go. So I'll paste that in. And I get plus or minus 2.5758 and change. That's plus or minus 2.576 if I round to 3 significant digits. Now, what's the issue here? The issue is that your Triola text has plus or minus 2.575. And that value is just wrong, and it's a typo. So when I do these problems, I use plus or minus 2.576, not the 2.575 that you'll see at various places in your text. This is muy no bueno. So that pretty much brings me to the end of my discussion in chapter 7. Let me give you or 7.1. Let me give you a bit of a summary. So in section 7.1, estimating a population proportion, we have that point estimate. P hat, that's equal to X over N. And then we have the, excuse me, the confidence interval. That's the P hat plus or minus the margin of error. That margin of error formula, that's that Z alpha over 2, P hat, Q hat, and all within the radical. And the tool that we use to take care of that is the one prop Z interval tool. We don't use the formula directly. We use the one prop Z interval, and you saw me demonstrate that quite a bit last night. There's videos up on the Canvas course shell that show this. The other thing that we did was sample size determination. You just saw the formulas, so I'm not going to write them down again, but you're going to have to use the formulas with that inverse norm tool to find the critical values for the formula. By the way, that's one of the main reasons I used that tool last night when I worked through that one example longhand before we got into the one prop Z interval. So the one prop Z interval and the inverse norm are the tools that we use here. We do have formulas for the sample size, but in general, your calculator handles pretty much all of this. So that's pretty much it. I'll probably run through a couple more examples on Wednesday when I do a final review of the Chapter 7 material. Tomorrow night, excuse me, Thursday. Tomorrow night, I'm going to do 7.2. So that's where I'll begin tomorrow night. So let me go ahead and stop my recording.